Hello, calculus fans. Let's work out the problem that we talked about in the previous video. We're going to make a rectangular box without a lid, and we're going to use only 48 square meters of material. What we'd like to do is find the dimensions of the box, height, length, and width, that will create the maximum volume. We have some freedom in how we're going to make the box. It could be wide and very shallow, or tall and very thin. So let's let X, Y, and Z be the length, width, and height of the box. Everything will be measured in meters. Our goal is to maximize the volume, which is X, Y, Z. And this is subject to the constraint where we say g of x, y, z is equal to 2xz plus 2yz plus xy equals 48. Notice that there's no coefficient of 2 on this one. That's because our box has no top. And so when we're measuring the surface area, we should not have a 2 there because there's only one measurement that has dimensions x times y. So we'll use the method of Lagrange multipliers. We're going to look for values of x, y, and z and lambda such that del v equals lambda del g and g of x, y, z equals 48. By the way, this lambda, when we go solve for things, we actually don't really care about what lambda is. That lambda is the thing that's called a Lagrange multiplier. Alright, so this gives us these equations. Vx equals lambda gx, Vy equals lambda gy, Vz equals lambda gz, and 2xz plus 2yz plus xy equals 48. Alright, so all these equations become yz equals lambda times 2z plus y, xz equals lambda times 2z plus x, xy equals lambda times 2x plus 2y. And then the constraint is the same. Now these are nonlinear equations, and there's really no general method for solving these. They can be very hard to solve. Here's a trick that works a lot. Notice that we can multiply both sides of the first equation by x, the second equation by y, and the third equation by z. And then the left-hand sides of those equations will be identical. They'll all be x, y, z. That means we'll be able to set things equal to each other. So if we do that, here's what we get. xyz equals lambda times 2xz plus xy. xyz equals lambda times 2yz plus xy. And then xyz equals lambda times 2xz plus 2yz. First of all, lambda should not be equal to 0. Because if lambda is equal to 0, then we would get that yz and xz and xy were all equal to 0, and that would make it impossible to fulfill the constraint. So we know that lambda is not equal to 0, and so we can set all those equal to each other, and we'll get 2xz plus xy equals 2yz plus xy equals 2xz plus 2yz. So if we take the first two expressions, we'll get 2xz equals 2yz. Now z can't be equal to 0. In fact, none of these variables can be equal to 0 because then the volume would just be nothing. It's not much of a box. So we know that x has to equal y. So the width and the length of the box have to be the same. The height might still be different. Now we'll take two different expressions that we know are equal, set them equal, and in a similar way we'll get y is equal to 2z. Again, we know that x is not equal to 0, so it can be canceled out. So let's put x equals y equals 2z into the constraint equation, 2xz plus 2yz plus xy equals 48, and then they all turn out to be the same thing. We get 4z squared plus 4z squared plus 4z squared equals 48. So if you solve that, you'd get plus or minus 2, but we don't care about negatives because these are measuring distances. So z is equal to 2, and so x and y have to be equal to 4. These are the dimensions in the box that give us the maximum volume. That's what we were looking for. There actually is no minimum on this, because if you wanted to, you could make a box that was really shallow, almost no height, and you could get the volume as small as possible. So we actually only have one critical number, and it leads us to the maximum. Okay, that's all for now.